System logic runs the modern enterprise, and for decades we've relied on a single language to map it out, the two-dimensional flowchart. These SciPoc models are highly efficient tools. They establish rigid logic boundaries, showing exactly where a system triggers and where it terminates. Systems analysts use these geometric maps to bring cross-functional teams to the table, creating a baseline consensus out of chaos. They are specifically designed to document the target state, the idealized workflow an organization intends to build. But they carry a hidden operational failure point. A 2D map is excellent at telling you when a step is supposed to occur. It is completely blind to what is physically or digitally happening inside that step. By optimizing for topological efficiency, these charts create a false sense of alignment, masking deep misunderstandings about the actual work required to run the system. You can see exactly where that consensus breaks down when you isolate a single process node. The geometry acts as a rigid container, but look inside the lines. It is a blank void. It defines the boundary, but entirely obscures the substance. Faced with an empty square, non-technical stakeholders are forced to independently guess the physical reality of the interface hiding inside that box. That ambiguity directly causes the friction, scope creep, and architectural rework that plague teams the moment they try to implement the target state. The directional arrows connecting the workflow are plotted with absolute precision, yet they point to boxes filled with total uncertainty. Solving this friction requires abandoning flat geometric shapes and building spatial environments instead. Large language models are currently being deployed to accelerate how we map these systems. Instead of dragging and dropping shapes, an AI agent parses raw domain constraints into machine-readable Markdown, generating the architecture instantly. This pipeline allows analysts to produce compliant 2D diagrams with near-zero latency. As the text changes, the topology reacts in real time. But generating a map faster does not solve the comprehension gap. To a non-technical stakeholder, a square generated by an algorithm is just as empty and abstract as a square drawn by a human. True cross-domain consensus requires taking that machine-generated text and using it to build a tangible reality. We achieve this by combining open web standards with emerging browser-based graphics processing. By tilting the process map and extruding into the z-axis, we break out of the flat topology and into a multi-dimensional workspace. The exact same machine-readable Markdown used to generate flat flowcharts can be pointed directly at a 3D rendering engine. The abstract square is replaced by a rendered target state workflow. This spatial environment translates topological theory into physical reality. You can clearly see the data handoffs and interfaces between the human operator and the automated machine. Stakeholders are no longer asked to interpret an arrow pointing to a blank box. They reach consensus immediately by observing the environmental reality of the system at work. Because this 3D environment is derived entirely from text-based Markdown, it behaves differently than an environment drawn manually in proprietary design software. It unlocks a mechanism called retroactive improvement, the ability to instantly propagate a lesson learned across all historical and future views of an asset. When an analyst updates the central machine-readable file, the 3D isometric target state shifts its geometry immediately. The AI agent recompiles the visualization on the fly. There is no manual redrawing and no exporting of new versions. Because this architecture lives on the web, anyone accessing the link sees the exact same hyper-accurate architecture, regardless of when they bookmarked it. A static system map becomes a canonical, living asset that scales precisely alongside the enterprise. Without this capability, organizations get trapped on an infinite staircase of manual updates, where analysts burn critical cycles explaining changes to a 2D map instead of optimizing the system. We are conditioned to treat system architecture as a static export, a document that is already out of date the second it gets published. We freeze our data into isolated, disconnected formats that require manual distribution to reach anyone. A web-first, computable architecture bypasses this historical bottleneck, offering zero latency agility. Maintaining dead, isolated architecture actively prevents an organization from adapting to complex changes in real time. Relying on static exports guarantees friction. while living architecture guarantees universal alignment. This capability is a return to the foundational promise of the World Wide Web, a universally accessible network of continuously updating information. 38 years ago, Tim Berners-Lee sketched out the concept of the hyperlink. It was designed to do exactly this, to scale human knowledge dynamically, without the friction of paper. By shifting from static topological modeling to AI-accelerated 3D environments, we can finally stop mapping workflows and start engineering computable territories. A single canonical web address can synchronize updates across an entire enterprise network, distributing millions of adjustments for less than a penny of compute. To achieve true cross-domain alignment, organizations have to abandon the representation trap of the two-dimensional shape and embrace the dimensional reality of the target state.